Okay, let's dive right into this. Welcome to today's explainer. We're taking a pretty fascinating journey into the quantum realm today. We're going to break down step by step exactly how one of the most famous quantum routines, Grover's algorithm, actually mechanically works. Now, our goal here isn't just to talk about abstract math, you know? We want to clearly visualize the physics and the logic driving the whole thing. To really understand why this algorithm is such a massive deal, I want you to imagine someone hands you a phone book with a million names in it. But there's a catch, and it's a big one. The book has been completely shredded and reassembled in totally random order. And you are looking for one specific person whose number is 5550173. There's no alphabetical structure, there's no clever shortcut you can take. You literally just have to start reading entries one at a time until you hit a match. On average, you're going to have to check half the book. In the worst case scenario, the whole thing. That painful brute force slog is exactly what computer scientists call unstructured search. Now, classically, there is simply no way around that grueling reality. It just keeps time. But Grover's algorithm, it's the quantum answer to that exact problem. Now, let's be clear, it doesn't make the search completely instant, but it does something truly remarkable. It finds the needle while only doing work proportional to the square root of the haystack's size. Think about what that actually means. A million entry search drops from roughly a million grueling steps to just about 1,000. It's an absolutely massive speed up. So let's build up exactly why that is possible. Okay, so a quantum computer with n qubits can represent n different configurations. The very first move in Grover's algorithm is to spread the system out, putting the machine into an equal blend of all of those possible configurations simultaneously. We do this by applying what's called a Hadamard gate to each qubit, and this creates what we call a uniform superposition. Every possible answer is now present in the state all at once, and each one carries a tiny equal sliver of amplitude, precisely 1 over the square root of n. Let's establish a mental visual for this, because it helps a lot. Picture a long row of identical bars, all standing at exactly the same modest height. One of those bars secretly corresponds to our target, the specific configuration we're hunting for. But right now, it looks exactly like all the rest. They're identical. The whole game of this algorithm is to find a way to grow that one target bar until it towers over the rest, so that when we finally measure the system, it overwhelmingly collapses to the exact answer we want. But here is the catch. You can't just peek at the bars to find the target. If you measure a quantum system right now, it instantly ruins the superposition. It collapses it and hands you nothing but a random guess. So whatever we do next has to be a very clever bit of physics. We need a mechanism that somehow knows which configuration is special and singles it out without us ever actually looking at it. This is where the oracle comes in. Think of the oracle as a sealed verifier. You absolutely cannot ask it, hey, what's the answer? But you can hand it a candidate, and it'll tell you yes or no. It asks, does this configuration satisfy the condition we're looking for? In the quantum world, we encode this verifier as a mathematical function that returns a 1 for our target and a 0 for absolutely everything else. So Grover's first active step uses this oracle to do something incredibly subtle. The oracle doesn't actually grow the target bar. Instead, it flips it upside down. The amplitude of the marked configuration gets its sign reversed, so it now dips beneath the floor, going below 0. Meanwhile, every other bar stays exactly where it was, completely flat. We call this phase inversion. Visually, imagine you've got a long, flat row of positive bars, and just one lonely bar poking downward. But wait, how do you flip only the right bar when you don't even know which one it is? Well, you do it through a brilliant trick called phase kickback. You bring in one extra helper qubit, prepared in a special state called the minus state. Now, this state has a really peculiar property. Flipping it actually multiplies it by -1. So you build a circuit with XOR logic that flips the helper qubit only when the main register holds a satisfying answer. Because of the strict rules of reversible quantum computing, that negative sign doesn't stay on the helper. It gets kicked back onto the amplitude of the marked configuration. The helper qubit emerges completely untouched, but our target's amplitude has quietly gone negative. The oracle has successfully tagged the answer without ever announcing it. Now, we do have a slight problem here. Simply flipping one bar negative hasn't actually made the answer any more likely to be found. Think about it. If you measured the system right now, that negative amplitude would still square to the exact same tiny probability it had before. The sign doesn't matter at all when you square it. So we still need a magic second step to actually amplify that target. And that brings us to the climax of the algorithm, the magic trick. It's a beautifully simple operation called inversion about the mean. Let's walk through exactly how this works. First, the quantum computer calculates the new average height of all the bars. Because one single bar is now pointing down in the negative, while the millions of others are positive, this new average line sits just a hair below the original uniform height. So the crucial point is this specific mathematical operation. Replace each amplitude with twice the average minus itself. Mechanically, what this formula does is reflect every single bar across that new, slightly lowered average line. And notice the immensely satisfying physical payoff here. A normal positive bar that was sitting slightly above the new mean gets reflected to sit slightly below it, meaning all the ordinary bars actually shrink a touch. But our target? It was sitting way down below the floor. When it gets reflected across that mean line, it gets violently flung way up high above everything else. In just one elegant move, the needle has grown and the hay has shrunk. Every single round of Grover's algorithm is just these two reflections back to back. Flip the target sign with the oracle, then mirror everything about the mean. Repeat. And this brilliantly illustrates a much wider mathematical truth. If you compose two reflections, it always produces a rotation. We can actually shift our perspective from bouncing bars to an elegant rotating arrow to see what is really happening inside the quantum state. Imagine the entire quantum state as a single arrow living in a flat plane. One axis points toward our target, and the other axis points toward everything else. The arrow starts out almost entirely horizontal, barely leaning toward the target at all. But each Grover round, each flip and reflect, nudges that arrow a fixed angle closer to the target axis. With each iteration, it swings away from everything else and points more directly at the correct answer. Do enough rounds, and the arrow points nearly straight at the answer, meaning a measurement will return the target with near certainty. But you've got to watch out for the hidden danger in this rotation analogy. A rotation doesn't just naturally stop on its own. Here's a surprising fact for you. If you get greedy and think, oh, more rounds equals better chances, you will absolutely ruin your search. If you keep applying iterations past the sweet spot, the arrow sails right past the target and starts swinging away again. Your probability of success climbs, it peaks, and then it literally falls right back down. Because of that, Grover's algorithm has an exact optimal stopping point, pi over 4 times the square root of n. This formula proves exactly how many iterations you need. You absolutely must stop near this number. If you run too few iterations, the answer is still buried in the hay. If you run too many, you've rotated right past the needle. That square root count is the entire incredible payoff. And what makes this so incredibly powerful is that the oracle is just a swappable black box. You only ever change the verifier inside. This exact same mathematical machinery, this universal rotation engine, can solve password cracking, complex satisfiability issues, intricate graph problems, or literally any search where you can recognize the correct answer when you see it. It completely redefines the limits of brute force. So, I want to leave you with this thought to ponder today. As quantum hardware matures, and we gain access to this universal rotation engine, armed with an unlimited supply of computational haystacks, what complex, impossible problem will humanity unlock first? Thank you so much for exploring this fascinating quantum mechanism with me. Catch you next time!